Hello everybody, my name is Narendra Kumar and we are from NRK Academy. Today we have this wonderful series in which we have got this chapter called Mechanics actually. This is a series called Physics Made Simple, and it has been written by me. The Wonder of Physics, Mechanics. So let's start. 1. Introduction. The origin of our understanding of motion or mechanics. Motion in physics means movement of bodies. This is the title actually. Introduction, the origin of our understanding of motion or mechanics. So this is the title, and now we begin. Motion in physics means movement of bodies. Here in this section we will look at motion or movement of solid bodies. When does a body move? Let us start with our own observations of things. When they move. The first kind of motion, and the one that strikes us first, is when one body hits another, isn't it? Or there is a push or a pull given to bodies. Examples: kicking a football, opening a door with your hand, striking a carrom coin, throwing a ball, etc., etc. These can be called contact forces in gross terms, because one body gross term became one body, because one body when striking another through actual contact does move the other body. Of course, the body to move must be light enough, should be light enough, and or the contact force applied must be strong enough. For example, a large rock cannot be moved by a man but can be moved by a crane, but a small rock can be moved by a man. These are the things that we observe. So we are looking at what we observe. We also observe things falling from a height when left free. Of course, birds and airplanes seem to go contrary to this, but that is a phenomenon involving air and its manipulation, and we won't go into that now, as in this section we are dealing with specifically motion involving solid bodies. And then we see the heavenly bodies moving, the sun rising in the east, moving across the sky and settling in the west. The moon also moves across the sky, but most people do not observe the moon moving as we sleep during that time. But we do see the moon at different places in the sky, isn't it? At different times, when we do happen to observe it during late nights and very early in the morning. We also see the countless stars. And among these are the planets that also look like stars, but are planets really. Usually people cannot, with their naked eye, distinguish between planets and stars. But the interesting thing is that to us, the planets move during the year actually. You can see some videos of that also. If you see the whole year, the planets are moving. If you locate it and observe it the whole year. But the stars don't seem to move. These are the observations. So planets, all the planets, the 8 planets actually move. Then we also see certain objects like magnets that move other objects like iron when brought near it. So we're talking about motion, isn't it? Travelers know another phenomenon, that if you hang a magnet or a compass needle is left free, it moves and points in a specific north-south direction. The Earth's magnetic field. These are our observations, and these same observations over a long period actually led the ancients to wonder and ask questions about these motions. Since we happen to see these things from childhood, and even photographs, and even now we have so many photographs, images and all from NASA, we take them for granted. Actually, we take them for granted. We tend to feel that it is like that because it is like that. Yet, there is a wonder to the observations just made. Setting aside contact forces for the moment, which are actually very complicated, let us consider bodies falling when left free from a height. Now, why should bodies fall at all? Really? After all, nobody is pushing it. You're just leaving it free. See the phenomenon as if you're seeing it for the first time. It is a wonder, really. Invariably, always, without fail, bodies fall on Earth if left free from a height. The apparent motion of the sun is even more wondrous and raises many questions. What is the sun? Why is there night and day? How far is it? Is the Earth moving or the sun moving? Why does it seem to move across the sky? Why is its apparent motion so regular? I'm saying apparent motion because we are taught in schools, right? We are taught from childhood, like the sun is the center and Earth is moving, but we see the sun moving. Why do the moon and the planets too move as seen by us? These questions were asked by the ancients. But some, the real seekers of knowledge, the real geniuses, the more passionate of them, did not only ask questions, they located the positions with the passage of time. It is equal to actually measuring the motion. They found no irregularities with respect to the sun and the moon. The sun and the moon went across the sky, rising from the east and setting in the west, as seen by us from the earth. There was no problem there. But one interesting thing is, when it came to the planets, they found a strange behavior of planets. Let us take, for example, Mars. There are many videos on YouTube on that also. When they observed Mars the whole year, they found Mars to go in one direction till June. And then strangely, it went backward for 3 months, like a spiral, and then went forward again, like they made a circle-like thing. This is how Mars looks to us. The same is true of all the other planets. This is called retrograde motion, which means backward motion. Now, the central question in the history of physics was asked, and that is the following. Is the Earth at the center and all planets, sun, moon, are moving around it, or is the sun the center and the planets move around it? Of course, in our schools we are told that sun is the center, but now I'm telling why, historically, how they came to that conclusion. If the Earth is at the center, right, the planets should move across the sky. Why is there backward or retrograde motion of the planets? That was a crucial kind of indication that something else is there. The ancient thinkers, especially Ptolemy, gave a system of Earth as a center and gave complicated motions to the planets to explain that retrograde motion, somehow to fit it into the data. But in the 16th century, it was Copernicus who got the actual real idea. He proposed that the sun is at the center and the planets are moving around the sun. He did this how? How did he prove it? By explaining backward or retrograde motion with his theory. Got it? If the sun is at the center, and let us take two planets, Earth and Mars, are going around the sun, you can imagine, then how will Mars look to people on Earth? I repeat, how will Mars look to people on Earth? Not really how it is, but how it will look to people on Earth. This was the question that Copernicus asked, really. It was a very interesting thing for me when I first read it. When Earth and Mars are side by side, let's say point A, and if Earth goes faster than Mars, like you can do it on the road also. You go faster than your friend who's also moving on the road, but you're going faster and you look back at him, then how will Mars look to people on Earth? It will seem to go backward, really. You can try it with your friend. Both of you go on a bike on the road. You go faster than him. He's also moving ahead. You're also moving ahead. But if you see him while moving, he's also moving. While moving, if you see him, he will look to you as if he's going backward. When Earth and Mars are as shown means side by side as shown in, and Mars is at the point B, that is opposite ends. Now, if it has gone other side, Mars and Earth are on the opposite sides, Earth will look to be going forward. So, at some period or some points on Earth, right? At some points or some period, Mars goes forward, seems to go forward, I mean here, and during some points and some period, it seems to go backward. Putting the sun at the center and the planets going around it is the only thing which explains the backward motion of all planets as seen from Earth. So that is how they understood, okay, so Earth is also moving. Now, of course, we know it very clearly. The planets are not going backward and forward. They are simply going around the sun. It seems to go like that only because Earth also is moving. That is the insight broadly we have given here. Now you can go to the videos and check it out. Hundreds of videos are there, and even about this retrograde motion. This is the insight we wanted to give you. Now this was a great turning point in understanding motion. Once we understood that sun is at the center, the next step was to state exactly with measurement, remember, as to how planets go around the sun. Kepler did that work and came up with his 3 Kepler's laws. Another great thinker, Galileo, came next and he measured free fall of bodies. His interest was not just observing free fall, but to measure how much distance it traveled while falling as time passed in successive seconds. He got the value of the acceleration, actually by experiment, as 9.8 meters per second square. This is what we learn in school also, the acceleration due to gravity. Now let us see how the picture looked at that time concerning motion. The sun was at the center and all the planets moved around it, including Earth. Things fell on Earth with an acceleration of 9.8 meters per second square. The planets moved around the sun according to Kepler's laws. But still the question still remained, right? Why did the planets move like that? Why did the acceleration on Earth of freely falling bodies have that value? It was then that the great genius, the greatest genius they call him, Newton, came on the scene. He thought intensely and deeply over the problem. Actually, they say during quarantine, he was in 6 months at his home. One day, the legend says he was walking in an apple orchard and he saw an apple falling, and it suddenly falling on him actually, and it suddenly occurred to him that the moon falling or being pulled to Earth by Earth is the same pull that Earth pulls on the apple. It's actually common sense in a way. Now, he further reasoned that the force is due to the product of the masses of moon and Earth and inversely proportional to the distance between the masses. What does this mean? There's the Earth pulls on the apple and the moon also. The force in the apple is directly proportional to the mass of the apple into mass of Earth. Inversely proportional to the square of the distance. That's the radius of the Earth. The force on the moon is directly proportional to the mass of the moon into mass of Earth. Inversely proportional to the square of distance. Which distance? That is the distance between the center of the Earth and moon. Newton could, now we can't go into mathematics here, Newton could with this insight derive Kepler's laws, and at one stroke Newton made Earth and heavens one. How did he make Earth and heavens one? He connected apple falling with moon falling. Moon actually falls, goes around like a satellite, while falling, while going ahead. He put all motion in the form of 3 laws of motion now and called the pull of gravity between the masses the universal law of gravitation. And he understood it's not just the apple falling, it's not just the moon falling, it's not just the planets getting attracted to the sun. Everything in the universe, just because it has mass, attracts everything else in the universe. This was amazing insight for me when I came out of school and in later life, because this was not how I was taught in school. That's why we are giving this insight here. Let us learn these 3 laws, these 4 laws systematically and mathematically. But before we go into it, we must understand certain concepts of motion in one dimension, because without concepts we can't understand and put it in a particular form. That will make our understanding of Newton's laws complete. The next section is on motion in one dimension. After that, we cover Newton's laws of motion and universal law of gravitation. Motion in one dimension is the next heading. 2.1. Distance and displacement. Now, look at the figure. There's a simple figure. So, Suresh begins at point A from his house and travels on the road and takes turns crossing many houses and reaching point B, his friend Ramdas's house. A bird from a terrace also moves in the air from the terrace of Suresh's house and goes to Ramdas's terrace in a straight line. The total distance traveled by Suresh is called distance. It has no direction. The straight line distance from the initial point A towards the final point B of the bird is called displacement. This is what usually is taught in school. It has direction also. The direction is from A to B. So simply put, if you go as a curve from A to B, it is distance. If you go straight line distance from A to B, it is called displacement, which also has direction. The figures 3 and 4 below illustrate this point further. Units of both distance and displacement are the same. It is a unit of length, meters, kilometers, all that. 10 millimeters equal 1 centimeter, 100 centimeters equal 1 meter, 1000 meters equal 1 kilometer. We know this. 1 feet is equal to 12 inches, 3 feet is equal to 1 yard. 2.2 is speed. We know what is speed when we look at 2 objects moving, right? We can tell which is going faster. Anybody in the world can say which is going faster if two bodies are moving. But what is involved in speed? How can we measure speed exactly? Physics is a lot about exact measurement also. Suppose 2 men come to you and the first man says, for example, I have traveled 100 meters. The second man says, I have traveled 100 meters, right? Just with this information, will we know who traveled faster? No. What else is required to know the faster of the 2 men? Yes, the men must specify the time also. So the first man says, I travel 100 meters in 50 seconds, let's say. Second man says, I travel 100 meters in 20 seconds. So first man traveled 100 meters in 50 seconds. Second man traveled 100 meters in 20 seconds. Why are we putting this so clearly and so obviously? I'll tell you in a minute. So first man went 100 meters in 50 seconds. Second man went 100 meters in 20 seconds. So in 1 second, averagely, first man traveled 100 by 50, 2 meters per second. 1 second is convenient. Second man traveled 100 by 25 meters per second. So second man is faster, right? In general, if someone or something travels d meters in t seconds, then in 1 second, obviously, speed is equal to distance by time. The unit is meters per second or feet per second or time per hour. Now, why we made it so clear is because students memorize that equation, speed is equal to distance by time. Actually, speed is equal to distance by time is actually not an equation. It is a concept. And now it is very clear why we have that and how we have it. This small thing enables you to understand physics suddenly very much better than before. Next 2.3 is velocity. Now velocity also is like speed only. Velocity 2 is speed, but velocity does not talk about distance. It talks about displacement, the shortest distance between 2 points. Not distance in 1 second. So velocity is equal to displacement by time. So velocity measures how much final net straight line distance the body traveled from initial to final point in 1 second. That is displacement divided by time. Example, if the displacement was 10 meters in 20 seconds, then in 1 second it will be 10 by 20, 1 by 2 meters per second. In general, velocity is equal to displacement by time. Now, next we got this concept called uniform speed. Uniform speed is simply constant speed, right? There is a body is covering equal distances in equal intervals of time. Example, a man is going on a scooter. His hand on the accelerator is steady. He is neither raising the accelerator nor lowering it. His speedometer shows 30 km per hour, 8.3 meters per second, let's say. Now, what does this mean? The meaning of it. It means that at every second he traveled 8.3 meters only, right? 1 second, 1 second, 1 second, 1 second, 1 second, 1 second, 8.3, 8.3, 8.3, 8.3, 8.3. I am putting it very clearly, so there will be no doubt about uniform velocity. This is the meaning of covering equal distances in equal intervals of time. So don't memorize. We don't have to memorize a certain definition. We should exactly understand it in reality. Now we come to average speed. Usually bodies do not go at uniform or constant speed, isn't it? At least on bikes. See the figure below. A caterpillar moves 1 second, 1 centimeter. 1 second, 2 centimeter. 1 second, 0 centimeters. It's just was stationary. The 4th second, 1 centimeter. 5th second, 1 centimeter. Caterpillar moved 1 centimeter in 1st second, 2 centimeters in second second, not 2 seconds. Again 0 centimeter in 3rd second, it stopped for a second, 1 centimeter in 4th second, 1 centimeter in 5th second, 3 centimeters in 6th second, 2 centimeters in 7th second. Now why are we putting it like this? So that again we don't have to memorize the concept of average speed. Now what is its speed? We will have to give 7 speeds here, isn't it? That is difficult, but I still want to know how fast the caterpillar traveled averagely. So we can take how much total distance it traveled in the total time. 10 centimeters in 7 seconds, so speed is equal to 10 by 7 centimeter per second. In general, average speed is equal to total distance traveled by total time taken. So we have uniform velocity, average velocity. Uniform velocity means that equal displacements take equal intervals of time. To find the average velocity, we use the formula average velocity is equal to total displacement by total time taken. Now we come to another topic called sign notation. Displacement and velocity. Being vectors have 2 signs for straight line motion. If we take a right side motion as positive, then the left side motion is negative. If we take upside motion as positive, then downside motion is negative. Let us see why. Let us see why we have this sign notation. Why is it so important? A man moves ahead for displacement in a straight line, 4 meters, and then moves back in the same straight line, 3 meters, right? So he moves 4 meters, then back 3 meters. This displacement from A to C is 4 meters. This displacement from A to B is minus 3 meters, opposite direction. Got it? So if you say forward direction is 4, backward direction is minus 3. Now 4 minus 3 is equal to 1 meter. The answer is correct. If we had not put the signs, we would have got 7 meters. Of course, the very obvious point. But many students miss this part. We need to have plus and minus for displacement. Forward means plus 4. Backward means minus 3. So the net is 1. But here, it would be a mistake to not put signs. It would have been wrong answer. So clearly displacement has positive and negative signs. That's a simple point here. So if you notice, we are kind of explaining it a little more clearly, because if you don't do that, you don't get the exact concept. And that's what we have done in all the other videos on sounds, liquids, atomic structure, electricity, everything. We have given the exact concept there. Once you get the concept, you are free, you are enlightened. A light bulb like thing comes and you become very strong in physics, by the way. Since velocity is only displacement, in 1 second, velocity too has positive and negative signs. So this is called vectors. So I have very briefly explained why we have vectors. Not that velocity and displacement are vectors. These are all covered in school syllabus. 2.8, acceleration, non-uniform and uniform acceleration. Now we come to another very interesting concept which very few people understand properly. In real life, usually a body changes its velocity, right? It may go faster, slower, or come to a stop. This is clear enough. This is called acceleration. But how do we measure this? Usually bodies do not go at a constant speed, as we saw in the caterpillar example. Suppose I am going on a bike. How do I go? I am at 20 km per hour now. Like if I look at my speedometer, I accelerate and reach 40 km per hour in 1 second. Then I stop at a red light. Then again I come to 20 km in 1 second. I raise the accelerator and so on. So here we have to give values and numbers at every moment, right? Like a graph. This is called non-uniform acceleration. I repeat, non-uniform acceleration, which means the speed is changing but not changing uniformly. There can be also uniform acceleration. Look at the following example. A body moves in the following way. 1 second, 1 second, 1 second, 2 meter, 4 meter, 6 meter, 8 meter. See, clearly you can see. In every second, 2 meters are added. It's going 2 meters extra. So in first second it moves 2 meters, second it moves 4 meters, third second, fourth second 8 meters, like that, isn't it? With each second the distance moved is 2 meters more than before. The change is like this is called uniform acceleration. If a body starts with a velocity of 2 meters per second and after 10 seconds reaches a velocity of 10 meters per second, then change in velocity is how much? 10 minus 2. In 10 seconds, isn't it? So it is 8 meters per second change in velocity in 10 seconds. I repeat, it is 10 minus 2 change in velocity in 10 seconds. So in 1 second, the change in velocity is 8 by 10, 0.8 meters per second change in 1 second. This is the concept which people miss. Okay. In general, if a body starts with the velocity of u and reaches a velocity of v in t seconds, but with uniform acceleration, the change in velocity is v minus u in t seconds. In 1 second, the change is v minus u by t. So a is equal to v minus u by t. It's simple mathematics here. Note that the above is true in uniform acceleration only. That is, change in velocity is same throughout the motion. Now, average velocity is u plus v by 2, isn't it? Average velocity. So displacement is equal to average velocity into time. Displacement, because average velocity is displacement by time. So u plus v by 2 into t. So when you manipulate it, u plus u plus at by 2 into t. S is equal to ut plus half at square minus 2. V is equal to u plus at and s is equal to ut plus half at square. T is equal to v minus u by a. So we can these are just equations derived for uniform accelerations. So this derivation we can actually skip. So we have derived equations for uniform acceleration. Now we come to Newton's laws and universal law of gravitation. Newton was a central figure in the history of physics. He was a person who made mechanics into a whole comprehensive science. He gave the fundamental statement to it. What is it that Newton said? Let us begin with his famous 3 laws of motion. Newton's first law. Every body remains at rest or of uniform motion in a straight line unless influenced by an external force, which means a body remains at rest if it is at rest. Okay, that's fine, isn't it? If you keep body at rest, it will be at rest. That goes with common sense and is pretty plain and obvious. But what about the second part? A body remains in uniform motion in a straight line unless disturbed by an external force. Is this true? On earth, if we see body stopping, even when nothing is stopping it, right? A ball rolled on a floor, after some time what happens? It comes to a stop by itself. Actually on earth the bodies are not free. This is the core concept. On earth the bodies are not free. Either the surfaces or air opposes any motion. When a body rolls on the floor, it is not really free because the roughness of the floor, which is called friction, is slowing it down. It is opposing the motion. This opposing force is called friction. But think of what would happen if there were no force opposing a moving body. A region like space where there are no bodies and no air would be a frictionless area. What if a body is given a small push and then left alone? Got it? You will actually see the body moving with the same speed and never stopping. Unless something stops it, and never going faster or slower unless something makes it go faster or slower. If a push is given in the same direction of its motion, it will go faster. If a push is given in the opposite direction, it will go slower. That's easy. If it is given at an angle, only then its direction will change. So this is true. A body remains at rest or in motion in a straight line unless it is influenced by some external force. You understand? In the universe as such, if there is no friction, the first law is true. A body by itself cannot change not only its state of rest but also of motion. It's a wondrous thing, isn't it? Why? Since childhood we are used to thinking that a body in motion will come to a stop ultimately. But now I hope you understand that it comes to a stop on earth only because of an opposing force called friction. That's why if the friction is less, say on a smooth floor, the body takes longer to come to a stop. Making friction zero and leaving the moving body totally undisturbed will make the body continue to move forever and ever and ever. You see, motion too is natural like rest. A body, this is a lovely concept, I love this concept. A body at rest will remain at rest. A body in motion will remain in motion. This is the principle of satellites and the motion of planets and moon, etc. They never stop. Nothing is opposing them. Once a particular motion had been given, was given, even will be given, there will be nothing to stop it. The earth once was given rotation around itself and revolution around sun, and it is doing the same thing and will do the same thing forever and ever and ever. This is the wonder. Give any motion to a body, it will be in that motion forever in the universe. We don't see it happening on earth because of surface friction. This is the simple point, right? Anybody can understand this, but this is how we wanted to present it. We will of course present it in greater detail in our advanced physics courses also. 3.2, Newton's second law. A force acting on a body accelerates it, right? Greater the force, greater the acceleration. Greater the mass of the object, the lesser the acceleration for the same force. Putting it another way, the acceleration of a body is directly proportional to the force. Obviously, suppose the body is moving, you put a force, it will move faster. That's all he's saying. And inversely proportional to its mass, which means the mass is more, the force required to move it will be less. If the mass is more, the force required will be more actually. So the force is inversely proportional to. So the acceleration depends on mass also. So it is more difficult to accelerate a greater mass. Directly proportional means if one is increased, the other increases proportionately. That is, if one is doubled, the second is doubled. If one is tripled, the second is tripled, and so on. This is the mass concept. Inversely proportional means if one is increased, the other is decreased proportionately. If one is doubled, the other is halved. When one is tripled, the other becomes 1/3. Let us try to understand the second law. A marble is at rest on a floor. If I push it, it moves. The marble is moving slowly on a floor. If I push it in the direction of the motion of the body, it goes faster. If I push it in the opposing direction, it goes slower. If I push it at an angle to its motion, it changes direction. So 4 things can happen to a body when a force is applied. 1, if already on motion, it can go from rest to motion, if it's at rest. 2, it can go faster. 3, it can go slower. 4, it can change direction, depending on the direction of the force. Same direction to the direction of the motion, it goes faster. Opposite direction of motion, it goes slower. At an angle to the direction of motion, it changes direction. Going faster or slower is called acceleration. But an interesting question arises here. Okay, a body goes faster, but how fast does it go faster? How fast does it go faster? This is not a silly question. A hard kick given to a football will make the ball go faster, very fast, at once. But if I continue to give a force slowly to a small ball for a long time, ultimately it will achieve a high speed, but it will have taken a longer time. A greater force makes a body go faster. A lesser force makes a body go faster, but slower when compared to a greater force. It's just a play of words. Hence, acceleration is not just change of speed, but the rate at which the speed is changing. Got the point? That is how fast it is changing. More force, faster, more quickly the speed will change. Lesser force, slower, more slowly the speed will change. You understand? Acceleration is a key concept in physics. So one part of Newton's second law simply says that greater the force, greater the acceleration. Lesser the force, lesser the acceleration. No force, no acceleration, that is rest or uniform motion. Newton's first law. So in a way, Newton's first law is contained in Newton's second law, in an obvious way. Now let us come to the second part of Newton's second law. Greater the mass, lesser the acceleration for the same force. That is, if certain force is applied to a body A and the same force is applied to body B, and if A is heavier than B, then which body accelerates more? Obviously B. In plain simple language, it is more difficult to change the speed of a heavier body than a lighter one. Greater force is needed to change the speed of a heavier body as compared to a lighter body. This is plain enough. So two things simultaneously determine the rate of change of speed, that is acceleration. Force and mass. Newton's third law. Every action has an equal opposite reaction and in the same straight line. In other words, if body A gives a force to body B gives at once an equal and opposite force to body A in the same direction. If you push the wall pushes you back. It will be quite funny if it doesn't. If you kick a stone, the stone will get the force, but you too will get it. You will be hurt. Got it? Force comes in pairs. There cannot be only a single force. An action force will get a reaction force at the same time. It's not actually reaction. They come together. Also, the reaction force is opposite and exactly in a straight opposite line. No. So 3.4 is fundamental force. So what are the forces? Okay, we are saying force. But what are the forces in nature? There are gravitational, electrical, magnetic and nuclear, weak and strong forces. Introduction. We have said that force causes acceleration, and greater the force, greater the acceleration. Proportionately, and lesser the force, lesser the acceleration. We also understand that for the same force, greater the mass, lesser the acceleration. But a great fundamental question still remains. Where do these forces come from? What is the origin? Forces cannot come from nothing. There has to be something that is the cause of the force, that is responsible for accelerations on masses. Forces can come due to mass of a body, gravitational forces. They can also come due to charge of a body, electrical forces. They can also come due to charges in motion, really. Magnetic forces, which you'll see in later chapters, the forces can originate in the nucleus of an atom, strong and weak nuclear forces. These forces are fundamental forces, and all other forces like friction, pushes and pulls, even pushes and pulls. That's very interesting. See, when you push a door, there's a lot of internal molecular repulsion that's actually happening. It's very complex. Tension on springs and strings, wind forces, muscular forces, all of them at root basically are caused fundamentally by these four forces. Okay, so this is just information. In the universe at large, basically four forces cause all motions, cause all accelerations on masses. So it's like you have got to know the universe kind of. These four forces, gravitational, electric, magnetic and nuclear forces exist due to mass, charge and motion originate in the nucleus respectively. We will discuss electrical, magnetic and nuclear force in later sections. Now we will consider only one force, gravitational force. 3.5 is gravitational force or the universal law of gravitation. This force is due plainly to masses of bodies. The very mass of a body in the universe has a power to attract another mass. Every mass attracts every other mass in the universe. When I first understood this, after I came out of college, it zapped me in a very bad way, in a deep way. Greater the masses, greater the force between them, and it's attractive. The masses come closer. Greater the distance, lesser the force between them. In fact, it is inversely proportional to the square of the distance. If the distance between two masses is doubled, the force reduces 4 times. If the distances are tripled, the force reduces 9 times, and so on. Gravitational force is a very weak force compared to electrical or magnetic forces. Masses attract surely, but one of the masses at least should be big enough for a visible acceleration. Two chairs near each other are actually attracting, but you don't see it getting attracted because because it's very weak. But if one chair becomes earth, the other chair would fall in it. On the moon too, an object falls, but since the mass of the moon is 1/6 of the earth, the force and hence the acceleration due to gravity is also 1/6. It falls slowly, like in slow motion. That is why on the moon it's like slow motion. In space, you must have seen in many movies also, or in real life spaceships and all, they show that. You can see hundreds of videos on that. In space, bodies float, they say. They're not actually floating, they're not falling. If a body is left alone, nothing happens, as it is very far away from any big object and negligible acceleration is observed. Because of negligible force, nothing happens to float. So a body in space left alone remains there. Which is like, it's like hanging. Nothing happens. It remains at rest because no force is acting on it. But our body is adapted biologically to gravitation. That is why it's very difficult to go to space. We have to have a full spaceship. It's a very complex object. It simply hangs there. Gravitational law discovered by Newton is a tremendously simple and a powerful fundamental fact of the universe. In the universe, masses attract. The whole of space science is explained. Almost all phenomena on a macroscopic level can be understood exactly, completely, beautifully by this law, and it's simple, and yet the implications and applications of this law staggers the mind. Makes one's breath stop, actually. Really, isn't it? The whole universe being ruled by one simple law. Every mass attracts every other mass. And because it's moving, they also keep moving, making crazy shapes and all that. And when they come closer, then the heat comes and all that we'll see in our next video, in another video called The Universe. And it blows the mind, actually, to use a common phrase. And that completes. Thank you so much. My name is Narendra Kumar and we are from NRK Academy. And I hope you basically understood it. You can see this video 2 or 3 times and you will have a wonderful feeling and interest in physics, and definitely you'll do very well in physics courses. Thank you so much.